Alright, so today I'm gonna be explaining another important paper with the title Can Graph Neural Networks Count Substructures? This Nurip's paper in 2020. The ability to detect and count certain substructures in graphs is important for solving many tasks on graph structured data, especially in the context of computational chemistry and biology, as well as social network analysis. Inspired by this, we propose to study the expressive power of graph neural networks via their ability to count attributed graph substructures, extending recent works that examine their power in graph isomorphism testing and function approximation. We distinguish between two types of substructure counting: induced subgraph count and subgraph count. So we proved that neither message passing neural networks nor second order invariant graph networks can count induced subgraphs. In this paper, they proved that MPNN and 2IGN can count subgraphs for star-shaped patterns. And then we prove that T iterations for KWL is unable to count induced subgraphs for path patterns. So we define an attributed graph as number of vertices. We have V edges, X and E. And unlike the node and edge features, the indices of the nodes are not inherent properties of the graph. Rather, different ways of ordering the nodes result in different representations of the same underlying graph. This is characterized by the definition of graph isomorphism. Two attributed graphs are isomorphic if there is a bijection between them. We define two types of counting associated with subgraphs and induced subgraphs. In this figure, you see that there are two types of substructures. In this figure, you see, and so the message passing neural network is a generic model that incorporates many popular architectures, and it is based on learning local aggregations of information in the graph. When applied to an undirected graph, an MPNN with T layers is defined iteratively as follows. And N is the neighborhood of node I. They have a theorem that says two attributed graphs that are indistinguishable by 2WL cannot be distinguished by any message passing neural network. And 2WL cannot induce subgraph count any connected pattern with three or more nodes. Another theorem is message passing neural network can perform subgraph count of star-shaped patterns. Also, another theorem says KWL at initialization is able to perform both induced subgraph count and subgraph count of patterns consisting of at most K nodes. Recently, diverging from the strategy of local aggregation of information as adopted by message passing neural networks and KWL, an alternative family of graph neural network models called invariant graph networks was introduced in these references, these invariant graph networks. So we restate its definition. First, note that if the node and edge features are vectors of dimension d sub n and d sub e respectively, then an input graph can be represented by second-order tensor B. If the nodes and edges do not have features, B simply reduces to the adjacent matrix. Thus, GNN models can be alternatively defined as functions in such second-order tensors. If two graphs are indistinguishable by 2WL, then no two IGN can distinguish them either. Now we talk about local relational pooling. Last video we talked about relational pooling. Now here is a little bit different. While deep message passing neural networks and two IGNs are able to aggregate information from multi-hop neighborhoods, our results show that they are unable to preserve information such as the induced subgraph counts of non-trivial patterns. To bypass such limitations, we suggest going beyond the strategy of iteratively aggregating information in an equivariant way, which underlies both message passing neural networks and invariant graph networks. One helpful observation is that if a pattern is present in the graph, it can always be found in a sufficiently large local neighborhood or egonet of some node in the graph. An egonet of depth L centered at a node I is the induced subgraph consisting of I and all nodes within distance L from it. For such a local mode, we adopt the relational pooling approach from Morphy. In summary, it creates a powerful permutation invariant model by symmetrizing a powerful permutation-sensitive model, where the symmetrization is performed by averaging or summing over all permutations of the nodes' orderings. So let this be the permutation-sensitive second-order tensor representation of graph G. Now, the relational pooling is defined like this. F is some function that is not necessarily permutation invariant. And this is B is transformed by permuting its two dimensions according to pi. And the summation quickly becomes intractable once n is large. As egonets are rooted graphs, we can induce the symmetrization over all permutations in S sub n. Now we consider models of this form, sigma of H sub I, where H sub I is this. And we propose to only consider ordered subsets of nodes in each egonet that are compatible with K-truncated BFS rather than all orderings of the full node set of the egonet. Using this dot, it means element-wise product between vectors. Now our model becomes like this. And this P tilde here is the index of a distinct node in ego graph. And this alpha is the normalization. So it's a normalization factor, which can depend on the degree of the nodes that appear in pi tilde. To adjust for the effect of adding irrelevant edges can alter the fraction of permutations in which a substructure of interest appears. We call this model depth L size K localized relational pooling. This LRP procedure can be applied iteratively in order to utilize multi-scale information. Now they define a deep version of that, and that's it. This is the performance on OGBG measured by ROC-AUC. And you see for different models like graph isomorphism, network, graph convolution, they compare it with their model for both training, validation, and test. Also, another data set zinc is, you can see the results here. Also for QM9,